Very exciting moment here. We got our first episode of Virtual Algebra 2 here on CroftTube, and our category is, we're talking about rational exponents today. So before we get started, a quick little bit of vocabulary. We've got words like index, radicand, and radical that we're going to be talking about a lot. I want to make sure we're clear on that. Index is this little number next to the radical sign. It tells you which root you want to find. So if you see something like this, that is the cube root or third root of it. Or maybe you've got the fourth root of it. Or maybe you've got just the square root of it, which you can leave like this, or you can write with a 2. Okay? But that's your index. Okay? Then you've got your radicand, which is the all-important number inside of the radical. That's what you're taking the root of. And of course, that square root looking symbol that we're used to seeing, that is what we call our radical. All right. So first rule, now we're talking about rational exponents, but really rational exponents is a fancy way to say fractional exponents, okay? It's the same thing here, and it's just saying, a number raised to a fraction of an exponent. Our rule here, first very important rule, is b to the 1 raised to the 1 over nth power, okay? And our rule says that b to the 1 over nth power is just the nth root of b. Okay, that's our rule. You take the denominator of the fraction and it becomes the index of your radical. Quick little proof on this, all right? Show why exactly this is happening. Not anything important you got to write down, but now we know the rules like x squared times x to the 5th. Okay, what you have is x times x times x times x, 5x is there. So what you do is you add those exponents to get x to the 7th. That's the rule that we have. If you look at something like rational exponents, though, and instead I'll change it up and say, okay, how about y to the 1/2 times y to the 1/2? You multiply those together, you're doing the same thing. You're adding your exponents, and you get y to the 1/2 plus 1/2 is 1, right? 2 halves make a whole, or just y. So, to prove what's going on here exactly, I'm going to carry the same equation down, but instead of y to the 1/2, I'm going to replace it with something else that it represents, and I know that it's going to be equal to, in the end, y. Now, the question you should ask yourself is what times itself makes y? Think about it. What times itself makes y? The answer should be the square root of y times the square root of y. Those two things multiplied together kind of cancel out those radicals and become just y. And if I put this into an equation here, boom, put the index in there, it's really the square root of y times the square root of y. So what I'm saying here is, all right, that means y to the 1/2 equals the square root of y. And that's kind of proving it with one specific example. Okay, let's go ahead and see some other examples to see why exactly that works. Again, key is our rule here. The denominator of our fraction becomes the index of our radical. Let's see our examples. X to the 1/2 power. Well, that's very similar to what I just did. The denominator here becomes the index. So I'm left with the square root of x, which I can put the 2 in there, or I can just leave it as square root of x, same thing. All right, pretty easy so far, right? Same thing here. Now, keep in mind, if we've looked at 2's in the denominator, it could be really any number. What if it's a 5? That means this number here becomes your radicand, the number inside, and the 5 becomes your index. There you go. And notice, I can't simplify that. 7 is a prime number. I'm certainly not going to be able to break that down anymore. All right, let's keep going. 16 to the 1/2 power is the same thing as the square root of 16. And we all know the square root of 16, make sure you simplify as much as possible. If you can, it's 4. Okay. Same thing now, 27 to the 1/3 power. Let's do it again. This number here becomes the index, while the 27 is my radicand. So 27, the cube root of 27, I'm going to simplify this the way we usually do. Cube root 27 is what times what? I'm going to say 9 times 3. That works. 9 is 3 times 3. And I'm prime factorized. I'm all good on that. Now I want to circle sets of 3 because my index is 3. And see how I got a perfect set of 3 without anything else left over. So the cube root of 27 simplifies to just 3. There's nothing left over, so I don't have to leave that radical. Cool. Make sure you got these written down. Make sure you're following along with me. We're going to bump it up a gear and keep going and learn some awesome stuff. Next part. So we got that part. The denominator of the fraction becomes our index. What we're doing now is we're making the fraction a little bit more complicated. Okay? So b to the m over n power. So this is a general form. And write this rule down. Write this whole thing when I reveal it down. Is the same thing as the nth root of b to the m. Or it's the same thing as the nth root of b raised to the m power. And I'm going to do a quick proof as to why exactly this works also. Okay? So make sure you write down this rule. You don't have to write down this proof, but just follow with me and then do the examples along with me as well. All right. So basic kind of order of operations stuff. Let's look at just m over n. What are other ways to represent that? M divided by n is the same thing as m times 1 over n, right? M divided by 2, for example, is the same as m times 1/2, right? It's also the same as 1 over n times m. I'm just switching the order of them there. It's the same thing either way I multiply it. Now let's prove why that's the same as these two expressions above, okay? Now I'm going to look back to this thing here. B to the m over n power, all right? I can rewrite this then based on what I said here. I can rewrite that b to the m times 1 over n power. Focusing on a little piece at a time, let's put parentheses around this. B to the m times the nth root, right? So simplifying this, I've got in my parentheses just b to the m. And then I've got that whole thing to the 1 over n power, which we just learned means turn it into this rather. You're finding the nth root of b to the m. And that is the first one you see here. All right? Let's do it the other way too. So I'm going back to the first one. B to the m over n. So any number raised to some fractional exponent, some rational exponent, is the same thing as b to the, let's rewrite it this way, 1 over n times m. And again, I want to focus on just one piece at a time. Let's focus on this piece first. B to the 1 over nth power. We already said, we rewrote that as the nth root of b. That's our rule, right? But then don't forget, you're raising that whole thing to the m power. And look at that, we're right back at that rule. So 2 quick proofs of it. Again, our key focus though is that when you have this rational exponent, the numerator now is the power that you raise it to, okay? The denominator is the index, okay? Let's see a couple examples and really cement this idea. X to the 2/3 power is the same thing, and I'm going to choose to rewrite this in that first form. You could really rewrite it either way. They're the same thing in the end, as the cube root of x squared. Again, this top of it there becomes my exponent inside the radical. The denominator becomes the index. Let's do another one. 25 to the 3/2 power. I'm going to choose to do this one the other way. So I'm going to say, all right, the square root of 25 to the 3rd. And once you see that, you might realize, oh, there's a reason why I did that. I can simplify this, and I can simplify the square root of 25 really easily. All right? Square root of 25 I know is 5, raised to the 3rd power, which is 125. Nice and simplified. There you go. Let's keep going. Now I've got 16 to the 3/4 power. So if I were to start writing this and say, okay, what about 16 to the third, the fourth root of that whole thing, I realized really quickly 16 to the third is going to be a big number, something like 4,000. It's going to be huge, right? Not something that I necessarily want to prime factorize. So instead, I'm going to rewrite it the other way. The fourth root of 16. Now, keep in mind, I could have done it that way, but I just really don't want to. Raise that to the third power. Now I know that the fourth root is 16. Well, let's double check to make sure. 16 is 4 times 4. 4 is 2 times 2. 4 is 2 times 2. I'm looking for sets of 4 because that's my index. And hey, look at that. So the fourth root of 16 is 2. And I'm going to raise it to the third power. 2 to the third is 8. Nice. That's an easier way to kind of simplify that out. And now it's curveball time. So I've got negative 8 to the 2/3, raised to the 2/3 power. Okay? To do this, I'm going to rewrite it. Negative 8 squared, and take the cube root of that. Now the reason why I'm squaring that inside is because when you square negative 8, hey, guess what? You're left with the cube root of 64. I like that. And the cube root of 64, you can break it down, prime factorize, but I know that's going to be 4. Cube root of 64. Very nice. Now, you might be asking yourself, though, what if I wrote that the other way? What if I went the cube root of negative 8 squared? Because you've seen problems before where you can't find the square root of a negative number. And you'd be right with that, but for this one, it's special. So let's look at one last thing, then you got some practice. Can you take the square root of a negative number? This is what we looked at before. Square root means like a little invisible 2 there. I'm just writing it in there because, well, that's what I like. And what you're asking there is, okay, what squared equals negative 1? That's what you're really asking yourself. And the reason why it doesn't work is because whenever you square anything, it becomes positive. So there are no real answers to this. Okay? It doesn't work. Now, you might remember, though, something we did put in here is I. It's an imaginary number, not a real solution, though. So you can't do that. But the other example we look at here, what about the cube root of negative 1? Can you do that? And what you should be looking at there is what cubed makes negative 1. In other words, so it's what cubed makes negative 1. But an easier way to see that, something cubed is just it times itself 3 times, right? Makes negative 1. So what is that answer? And I'm going to say, what if you put a negative 1 in there? Negative 1 times negative 1 times negative 1. Now, these two negatives become positive because 2 negatives make a positive, but you're left over with 1 more negative because it's an odd root. So your answer to the cube root of negative 1 is negative 1. Okay? To see one other quick example, what about like the cube root, the one we're about to do, of negative 8? In other words, what thing times itself 3 times makes negative 8? What times what times what makes negative 8? That value is going to be negative 2, and let's see why. Negative 2 times negative 2 times negative 2. Negative 2 times negative 2 is positive 4, and then you got positive 4 times negative 2 gets you negative 8. Okay, so in summary here, the reason why that works is if the index is an odd number, you can take the root of a negative number. Because you're multiplying an odd number of things together, you're going to have a negative left over. Okay, guys, so we've got our rules of rational exponents here. These are going to be your practice problems, okay? I want you to start out by expressing the expressing them as rational or fractional exponents, then express them as radicals, then convert to radicals and simplify completely using the strategies we know. Okay, so pause the video, try out these, 12 problems, and then I'm going to show you the answers. Pause it. All right, here are your answers, possibly. Check them out, see how you did. Make sure you've written all this down on a piece of paper, and you're going to hand this in for a grade. Awesome job today, guys. Good talking to you. See you out there.